Okay, good morning. So today we're going to continue our exploration of multi-threaded algorithms. Last time we talked about some aspects of scheduling and a little bit about linguistics to describe a multi-threaded computation. And today we're going to actually deal with some algorithms. So we're going to start out with a really simple thing. Actually, what's fun about this actually is that everything I'm going to teach you today, I could have taught you in week 2. Okay, because basically it's just, taking the divide and conquer hammer and just smashing, problem after problem with it. Okay, and actually next week's lecture is on caching, also very similar. Okay, so everybody should bone up on their master theorem and substitution methods for recurrences and so forth, because that's what we're going to be doing. And of course, all this stuff will be on the final. So we'll start with matrix multiplication. And we'll do n by n. So our problem is to do C equals A times B. And the way we'll do that is using divide and conquer, as we saw before, although we're not going to use Strassen's method. Okay, we'll just use the ordinary thing, and I'll leave Strassen's as an exercise. So the idea is we're going to look at matrix multiplication in terms of an n by n matrix in terms of n over 2 by n over 2 matrices. So I partition C into 4 blocks, and likewise with A and B. Okay, and we multiply those out, and that gives us the following. Make sure you get all my indices right. Okay, so it gives us the sum of these two n by n matrices. Okay, so for example, if I multiply the first row by the first column, I'm putting the first term, A11 times B11, in this matrix, and the second one, A12 times B21, gets placed here. So when I sum and so forth for the other entries, and when I sum them, I'm going to get my result. So we can write that out as a, let's see, not sure this is going to all fit on one board, but we'll see what we can do. Okay, so we can write that out as a multi-threaded program. So this, we're going to assume that n is an exact power of 2 for simplicity. And since we're going to have 2 matrices that we have to add, we're going to basically put one of them in our output C. That'll be the first one, and we're going to use a temporary matrix T, which is also n by n. And the code looks something like this. Okay, if n equals 1, then C of 1 gets A of 1, 1 times B of 1, 1. And otherwise, what we do then is we partition the matrices. Okay, so we partition them into the blocks. So how long does it take me to partition a matrix into blocks if I'm clever in my programming? Yeah. No time, or it actually does take a little bit of time. Yeah, order 1, basically. Okay, because all it is just index calculations. You have to change what the index is. You'd have to pass in, when you're passing these in addition to A, B, and C, for example, pass in a range, which would have essentially a constant overhead. But it's basically order 1 time. Basically order 1 time, okay, to partition the matrices, because all we're doing is index calculations. Okay, and all we have to do is, just as we go through, is just make sure we keep track of the indices. Okay? Any questions about that? People follow? Yeah? Okay. Okay, just, that's sort of standard programming. So then what I do is I spawn multiplication of, of the submatrices. And spawn continues C21 gets A21, B11, and 2, and then C22 gets A21. Okay, and continuing on to the next page. Let me just make sure I somehow get the indentation right. So this is my level of indentation, and I'm continuing right along. And now what I do is put the results in T. Okay, so I spawn off all these multiplications. So that means when I spawn, I get to after I spawn something, I can go on to the next statement, okay, and execute that even as this is executing. Okay, so that's our notion of multi-threaded programming. I spawn off these 8 things. What do I do next? What's the next step in this code? Sync, yeah. Okay, I got to wait for them to be done before I can use their results. Okay, so I put a sync in, saying wait for all those things I spawned off to be done. And then what? Yeah, then you have to add T and C. So let's do that with a subroutine call. Okay, and then we're done. We do a return at the end. Okay, so let's write the code for add, because add we also would like to do in parallel if we can. And what we're doing here is doing C gets C plus T. Okay, so we're going to add T into C. So we have some code here to do our base case and partitioning, because we're going to do it with divide and conquer as before. And this one's actually a lot easier. We just spawn add of C11, T11, n over 2, C12, T12, n over 2, C21, T21, n over 2, C22, T22, n over 2, and then sync and return the result. Okay, so all we're doing here is just dividing it into 4 pieces, spawning them off. That's it. Okay, wait till they're all done, then we return with the result. Okay, so any questions about how this code works? So remember that here we're going to have a scheduler underneath, which is scheduling this onto our processors, and we're going to have to worry about how well that scheduler is doing it. And from last time, we learned there were 2 important measures, okay, that can be used essentially to predict the performance on any number of processors. And what are those 2 measures? Yeah, T1 and T infinity, so that we had some names. T1 is the work, good, and T infinity is critical path length, good, okay? So you have the work and the critical path length. If we know the work and the critical path length, we can do things like say what the parallelism is of our program, and from that understand how many processors it makes sense to run this program on. Okay? So let's do that analysis. Okay, so let's let m sub p of n be the p processor execution time for our mult code, and a sub p of n be the same thing for our matrix addition code. So the first thing we're going to analyze is work. And what do we hope our answer to our work is? When we analyze work, what do we hope it's going to be? Well, we hope it's going to be small. Grant you that. Okay. What could we benchmark it against? Yeah, if we wrote just something that didn't have any parallelism. Okay? We'd like our parallel code when run on one processor to be just as fast as our serial code, the normal code that we would write to do this problem. That's generally the way that we would like these things to operate. Okay? So let's see. So what is that for matrix multiplication in the naive way? Yeah, it's n cubed. Of course, if we use Strassen's algorithm or one of the other faster algorithms, we can beat n cubed. But for this problem, we're just going to focus on n cubed, and I'll let you do the Strassen as an exercise. So let's analyze the work. Okay, since we have a subroutine for add that we're using in the multiply code, okay, we'll start by analyzing the add. So we have a1 of n, okay, is, well, can somebody give me a recurrence here? What's the recurrence for understanding the running time of this code? Okay, this is week 2? This is lecture 1, actually. This is like lecture 2, or at worst, lecture 3.
T equals 4 T of n.
Well, a of 1 of n.
A of 1 equals 4 A of 1 n over 2.
Plus order 1, right. Okay, that's right. Okay, so we have 4 problems of size n over 2 that we're solving. Okay, so to see this, you don't even have to know that we're doing this in parallel, because the work is basically what would happen if it executed on a serial machine. So we have 4 problems of size n over 2 plus order 1 is the total work. Any questions about how I got that recurrence? Is that pretty straightforward? Okay, if not, let me know. Okay? And so what's the solution to this recurrence? Dun, 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 dun. Yeah, order n squared. How do we know that? Yeah, master method. So n to the log base 2 of 4, right, is n squared. Compare that with order 1. This grammatically dominates. So this is the answer, the n to the log base 2 of 4, n squared. Okay, everybody remember that? So I want people to bone up, because this is going to be, recurrences and divide and conquer stuff is going to be on the final. Okay, even though we haven't seen it in many moons. Okay, so that's good. That's the same as a serial. If I have to add 2 n by n matrices, how long does it take me to do it? N squared time. Okay, so input is size n squared. So you're not going to beat the size of the input if you have to, look at every piece of the input. Okay, let's now do the work of the matrix multiplication. So once again, we want to get a recurrence here. So what's our recurrence here? Yeah?
4 and 1 n over 2.
Not quite. 8, right. Good. Okay. 8 m1 n over 2 plus, yeah, there's theta n squared for the addition, and then there's extra theta 1 that we can absorb into the theta n squared. Isn't asymptotics great? Okay, it's just great. Okay. So, and so what's the solution to that one? Theta n cubed, how do we have that? Why is that? Man, we're exercising old muscles, aren't we? And they're just creaking. I can hear them. Okay, why is that?
Master method.
Yeah, master method, because we're looking at, what are we comparing?
N cubed, and that's correct.
Yeah, n to the log base 2 of 8, or n cubed, versus n squared. This one dominates, order n cubed. Okay? So this is same as serial. This was the same as serial. This was the same as serial. That's good. Okay, we know we have a program that on one processor will execute the same as a serial, as our serial code on which it's based. Namely, we could have done this if I had just gotten rid of all the spawns and sinks. That would have just been a perfectly good piece of pseudocode describing the runtime of the algorithm, describing the serial algorithm, and its runtime would be ends up being exactly the same. Not too surprising. Okay? Okay, so now we do the new stuff. Critical path length. Okay? So here we have a infinity of n. Ooh. Okay, so we're going to add up the critical path of this code here. How do I figure out the critical path of a piece of code like that? So it's going to expand into one of those DAGs. What's the DAG going to look like? How do I reason? So it's actually easier not to think about the DAG, but just simply think about what's going on in the code. Yeah?
Since all those spawns are the same, just look at if you had only one.
Yeah, so it's basically, since all 4 spawns are spawning off the same thing, and they're operating in parallel, I can just look at one. Or in general, if I spawned off several things, I look at whichever one is going to have the maximum critical path for the things that I've spawned off. So when we do work, we're usually doing plus when I have multiple subroutines. When we do critical path, I'm doing max. It's going to be the max over the critical paths of the subroutines that I call. Okay, and here they're all equal. So what's the recurrence that I get? What's the recurrence I'm going to get out of this one? Yeah, a infinity n over 2 plus constant. Okay, because this is what the worst is of any of those 4, because they're all the same. They're all a problem looking at the critical path of something that's half the size, of a problem that's half the size. Okay, people with me? Okay, so what's the solution to this? Yeah, that's theta log n. That's just, once again, master theorem case 2. Because the solution to this is n to the log base 2 of 1, which is n to the 0. So we have, on this side, we have 1, and here we're comparing it with 1. They're the same, so therefore we tack on that extra log n. Okay, so tack on 1 log n. Okay, so case 2 of the master method. Pretty good. Okay, so that's pretty good because the critical path is pretty short. Log n compared to the work, n squared. Okay, so let's do then this one, which is a little bit more interesting, but not much harder. How about this one? What's the recurrence going to be? Critical path of the multiplication. So once again, it's going to be the maximum of everything we spawned off in parallel, which is, by symmetry, the same as one of them. So what do I get here? M infinity of n over 2 plus theta log n. Where'd the theta log n come from?
From the addition.
Yeah, from the addition, that's the critical path of the addition. Now, why isn't that the maximum of that with all the spawns? We said that when you spawn things off, you're going to do them.
You sync all those spawns.
Yeah, you sync first. And sync says you wait for all those to be done, so you're only taking the maximum, and across syncs, you're adding. So you add across syncs, and across things that you've spawned off in parallel, that's where you're doing the max. Okay? But if you have a sync, it says, whoop, that's the end. You've got to wait for everything there to end. This isn't going on in parallel with it. This is going on after it. So whatever the critical path is here, okay, if I had an infinite number of processors, I'd still have to wait up at this point, and that would therefore make it so that the remaining execution here was whatever the critical, I would have to add whatever the critical path was to this one. Is that clear to everybody? Okay. So we get this recurrence, and that has solution what?
Log squared.
Yeah, theta log squared n. once again, by master method case 2, where this ends up being a constant versus log n. Those don't differ by a polynomial amount, but in fact are equal to a log factor. And what we do in that circumstance is tack on an extra log factor. Okay, so as I say, good idea to review the master method. Okay, that's great. So now let's take a look at the parallelism that we get. We'll just do it there. For the multiplication. Okay. So parallelism is what? For the multiplication. What's the formula for parallelism? So we have P bar is the notation we used for this problem. What's the parallelism going to be? What's the ratio I take? Yeah, it's m1. So it's m1 of n divided by m infinity of n. Okay? And that's equal to, that's n cubed, that's n squared. Or log n squared, sorry. Log squared n. Okay? So that says this is the parallelism. That says you could run up to this many processors and expect to be getting linear speed up. If I ran with more processors than the parallelism, I don't expect to be getting linear speed up anymore. Okay, because I'll hit the bound. What I expected to run in is just time proportional to the critical path length. And throwing more processors at the problem is not going to help me very much. Okay? So let's just look at this just to get a sense of what's going on here. Let's imagine that the constants are irrelevant, and we have, say, 1,000 by 1,000 matrices. Okay, so in that case, our parallelism is 1,000 cubed divided by log of 1,000 squared. What's log of 1,000? 10, approximately, right? Log base 2 of 1,000 is about 10, so that's 10 squared. So you have about 10 to the 7th parallelism. How big is 10 to the 7th? 10 million processors. Okay? So who knows of a machine with 10 million processors? What's the most number of processors anybody knows about? Yeah, not quite. Blue Gene has, the IBM Blue Gene has humongous number of processors up in the 10, exceeding 10,000. Okay? Yeah. Those were 1-bit processors. Okay, so this is actually a pretty big number. And so, you know, our parallelism is much bigger than a typical actual number of processors. So we would expect to be able to run this and get very good performance. Okay, because we're never going to be limited in this algorithm by performance. However, there are some tricks we can do. One of the things in this code is that we actually have some overhead that's not apparent because I haven't run this code with you, although I could, which is that we have this temporary matrix T. And we can, you know, if you look at the execution stack, we're always allocating T and getting rid of it, etc. And one of the things when you actually look at the performance of real code, which is now that you have your algorithmic background, you're ready to go and do that with some insight. Of course, you're interested in getting more than just asymptotic behavior. You're interested in getting real performance behavior on real things. So you do care about constants in that nature. Okay? And one of the things is having a large temporary variable, that turns out to be a lot of overhead. And in fact, it's often the case when you're looking at real code that if you can optimize for space, you also optimize for time. If you can run your code with smaller space, you can actually run it with smaller time. It tends to be a constant factor advantage, but those constants can add up and can make a difference in whether somebody else's code is faster or your code is faster, okay, once you have your basic algorithm. So the idea is to, in this case, we're going to get rid of it by trading parallelism, because we got oodles of parallelism here, for space efficiency. Okay, and the idea is we're going to get rid of t. Okay, so let's throw this up. So who can suggest how I might get rid of t here? Get rid of this temporary matrix. Yeah.
Well, could you do it by, for the base case, you change it to adding it to whatever's already in C. And
Okay.
then for the last four calls to mult, you change it from T to C, and then you get rid of the add.
So if you just did adding it into C. So the issue that you get there, if they're both adding into C, is you can get interference between the two subcomputations. Now, there are ways of doing that that work out, but you now have to worry about things we're not going to talk about, such as mutual exclusion, to make sure that as you're updating it, somebody else isn't updating it and you don't have race conditions. But you can actually do it in this context with no race conditions.
Well, you could add another sync before the second set of four spawns then.
Yeah, exactly. Okay, exactly. So the idea is spawn off 4 of them. Okay, they all update their copy of C, and then spawn off the other 4 that add their values in. So that's is a piece of code we'll call mult_add. And it's actually going to do C gets C plus A times B. Okay, so it's actually going to add it in. So initially you'd have to zero out C, but we can do that with code very similar to the addition code in with order n squared work and order log n critical path. So that's not going to be a big part of what we have to deal with. Okay. So here's the code. We basically, once again, do the base and partition, which I'm not going to write out the code for. And then we spawn a mult_add of C11, A11, B11, and over 2. And we do a few more of those down to the 4th one. And then we put in a sync. And then we do the other 4. And down to and then sync when we're done with that. Okay? Does everybody understand the code? See that it basically does the same calculation. We don't actually need to call add anymore because we're doing that as part of the multiply because we're adding in, but we do have to initialize. Okay, we do have to initialize the matrix in this case. Okay, so there is another phase. So people understand the semantics of this code. So let's analyze it. Okay, so what's the work of multiply add of n? It's basically the same thing, right? It's order n cubed because the serial code is almost the same as the serial code up there. Okay, not quite. Okay, but you get essentially the same recurrence, except you don't even have the add. You get the same recurrence, but with order 1 here. Whoops, order 1 up here. So it's still got the order n cubed solution. Okay, so that, I think, is not too hard. Okay, so the critical path length. So there, let's write out our, so multiply add of n. Okay, what's my recurrence for this code?
You have 2 because you have to wait for the
Yeah, so
2 m infinity n over 2. Plus we lost that, so order 1.
Plus order 1, yeah. Okay, so the point is that we're going to have, for the critical path, we're going to spawn these 4 off, and so I take the maximum of whatever those is, which, since they're symmetric, is any one of them. Okay, and then I have to wait, and then I do it again. So that sync, once again, translates into, in the analysis, it translates into a plus of the critical path. Whereas the things I spawn off in parallel, I do the max. Okay? So people see that? So I get this recurrence, 2ma of n over 2 plus order n, and so it's for order 1. And what's the solution of that? Yeah, that's order n. Okay? So because n to the log base 2 of 2 is n, and that's bigger than 1, so we get order n. Okay? So the parallelism we have p bar is equal to ma1 of n over ma infinity of n is equal to, in this case, n cubed over n, or order n squared. Okay, so for 1,000 by 1,000 matrices, for example, by the way, 1,000 by 1,000 is considered a small matrix these days, because that's only 1,000,000 entries. Put that on your laptop, no sweat. Okay, so, but for 1,000 by 1,000 matrices, our parallelism is about 10 to the 6th. Okay, so once again, ample parallelism for anything we would run it on today. And as it turns out, it's faster in practice. Because we have less space. Okay, so here's a game where, so often the game you'll see in theory papers, if you look at research papers, people are often striving to get the most parallelism. And that's a good game to play. Okay, but it's not necessarily the only game. Particularly if you have a lot of parallelism, one of the things that's very easy to do is to retreat on the parallelism and gain other aspects that you may want in your code. Okay, and so this is a good example of that. In fact, and this is an exercise, you can actually achieve work n cubed, order n cubed work, and a critical path of log n. So even better than either of these two algorithms in terms of parallelism. Okay, so that gives you n cubed over log n parallelism. So that's an exercise. And then the other exercise that I mentioned that's good to do is parallel Strassen. Okay, doing the same thing with Strassen and analyze what's the work and critical path and parallelism of the Strassen code. Okay? Any questions about matrix multiplication? Yeah.
You mentioned initialization for alternate.
Yeah, so that would add a log n to the critical path, which is nothing compared to the n.
What do you do exactly?
Excuse me?
What is initialization?
Well, you've got to make sure c is 0 to begin with.
Oh, right.
Okay, so just you have to set all the entries to 0, and so that will take you n squared work, which is nothing compared to the n cubed work you're doing here, and it'll cost you log n additional to the critical path, which is nothing compared to the order n that you're spending. Okay, good. Any other questions about matrix multiplication? Okay, as I say, this is all like goes back to week 2 or something in the class. Do you have a comment?
Is there an easy measure under which the first algorithm has more space than the second algorithm? Can you quantify that?
Yes, you can. Okay. Yes, you can. It's actually kind of interesting to look at that. Actually, we can talk later. Okay, we'll write a research paper after the class is over. Okay, because there's actually some interesting open questions there. Okay. Let's move on to something that you thought you had gotten rid of weeks ago, and that would be the topic of sorting. Back to sorting. Okay, so we want to parallel sort now. Okay, hugely important problem. So let's take a look at, so if I think about algorithms for sorting that sound easy to parallelize, which ones kind of sound easy to parallelize? Quicksort, yep, that's a good one. Yep, quicksort is pretty good one to parallelize and analyze. But remember, quicksort has a little bit more complicated analysis than some other sorts. What's another one that looks like it should be pretty easy to parallelize? Merge sort, okay. Like, when did we teach merge sort? Day 1. Okay, so we'll do merge sort, okay, because it's just a little bit easier to analyze. Okay, we could do the same thing for quicksort. So here's merge sort. Okay, and it's going to sort A of P up to R. So if P is less than R, then we get the middle element. And then we'll spawn off, since we have to, as you recall, when you merge sort, you first recursively sort the two subarrays. There's no reason not to do those in parallel. Let's just do them in parallel. Let's spawn off merge sort of A, P, Q. And spawn off then merge sort of A, Q plus 1, R. And then we wait for them to be done. Sync. Don't forget your syncs. Okay? You sink or swim. Okay? And then what do we do when we're done with this? Okay? We merge. Okay? So we merge of A, P, Q, R, which is merge A of P up to Q with A of Q plus 1 up to R. Okay, and once we've merged, we're done. Okay, so this is the same code as we saw before in day 1, okay, except we've got a couple spawns and a sink. So let's analyze this. So the work, let's call it T1 of n, is, what's the recurrence for this? This really is going back to day 1, right? We actually did this on day 1 of this class. Okay, so what's the recurrence? 2t1 of n over 2 plus order n. Merge is an order n time operation. Okay? And so that gives us a solution of n log n. Okay? Even if you didn't know the solution, you should know the answer. Okay? Which is the same as the serial code, not surprisingly. That's what we want. Okay? Critical path length, okay, t infinity of n is equal to, okay, t infinity of n over 2 plus order n again. And that's equal to order n. Okay? So the parallelism is then p bar equals t1 of n over t infinity of n is equal to theta of log n. Okay. Is that a lot of parallelism? No, that's what we have a technical name for that. We call it puny. Okay. That's puny parallelism. Log n. Now, so this is actually probably a decent algorithm for some of the small-scale processors, especially the multi-core processors that are coming on the market, and some of the smaller SMP, symmetric multiprocessors that are available. You know, they have 4 or 8 processors or something. Might be okay. There's not a lot of parallelism. Okay, it's you know, for a million elements, log n is about 20. Okay, so, and then there's constant overheads, etc. This is not very much parallelism at all. Question?
How would you expect to do better? It's one of your critical path always be at least omega n.
Yeah. So how can we do better? I mean, it's like, man, that merge, right, takes order n. If I want to do better, what should I do? Yeah? Sort in place, but for example, if you do quick sort and partition, you still have a linear time partition. So you're going to be very much in the same situation. So what can I do here? Parallel merge. Okay, let's make merge go in parallel. That's where all the critical path is. Let's figure out a way of building a merge program that has a very short critical path. Okay? You have to parallelize the merge. This is great. You guys are... It's so nice to see at the end of a course like this that, you know, people have the intuition for, you know, oh, you can look at it and sort of see where should you put in your work. Okay, the one thing about algorithms is it doesn't stop you from having to engineer a program when you code it. There's a lot more to coding a program well than just having the algorithm, as we talked about also in day 1. There's things like making it modular and making it maintainable and a whole bunch of things like that. But one of the things that algorithms does, it tells you where should you focus your work. Okay? There's no point in, for example, sort of saying, okay, let me spawn off 4 of these things of size n over 4 in hopes of getting, you know, I mean, it's like, that's not where you put the work. You put the work in the merge because that's the one that's the bottleneck. Okay? And that's the nice thing about algorithms is it very quickly lets you hone in on where you should put your effort. Okay, when you're doing algorithmic design in engineering practice. So we must parallelize the merge. The merge routine. So here's the basic idea we're going to use. So in general, when we merge, when we do our recursive merge, we're going to have 2 arrays. Let's call them A and B. I called them A there. Probably shouldn't have used A. I probably should have called them something else, but that's what my notes have, so we're going to stick to it. Let me give a little bit more space there. Let's see what's going on. We have 2 arrays. I'll call them A and B. Okay. And what we're going to do, these are going to be already sorted. And our job is going to be to merge them together. So what I'll do is I'll take the middle element of A. So this, let's say, goes from 1 to L. And this goes from 1 to M. Okay? I'll take the middle element, the element at L over 2, say. And what I'll do is use binary search to figure out where does it go in the array B. Where does this element go? And it goes to some point here where we have J here and J plus 1 here. So we know, since this is sorted, that all these things are less than or equal to A of L over 2. And all these things are greater than or equal to A of L over 2. And similarly, since that element falls here, all these are less than or equal to A of L over 2. And all these are going to be less than or greater than or equal to. Okay? And so now what I can do is, once I've figured out where this goes, I can recursively merge this array with this one, and this one with this one, and then if I just concatenate them all together, I've got my merged array. Okay? So let's write that code. Everybody get the gist of what's going on there? How we're going to parallelize this merge? Of course, you can see it's going to get a little messy because, you know, J could be anywhere. Here's my code, parallel merge of and we're going to put it in C of 1 to n. So I'm going to have n elements. So this is doing merge A and B into C, and n is equal to L plus m. Okay, so we're going to take 2 arrays and merge it into the 3rd array. Okay? So let's see. Without loss of generality, I'm going to say L is bigger than m, as I showed here, because if it's not, what do? Just do it the other way around, right? So I figure out which one is bigger. So that only costs me order 1 to test that or whatever. And then I basically do a base case. You know, if the 2 arrays are, you know, empty or whatever, what you do in practice, of course, is, you know, if they're small enough, you just do a serial merge. Okay? If they're small enough, and I don't really expect to get much parallelism, there isn't much work there, might as well just do a serial merge, be a little bit more efficient. Okay? So do the base case. So then what I do is I find the j such that b of j is less than or equal to a of L over 2, less than or equal to b of j plus 1, using binary search. When did we cover binary search? Oh, yeah. That was week 1, right? Is that in first recitation or something? Yeah. It's amazing. Okay. And now what we do is we spawn off P merge of A of 1 L over 2, B of 1 to J, and stick it into C of 1 to L over 2 plus J. Okay. And similarly now we can spawn off a merge of A of L over 2 plus 1 up to L, B of J plus 1 up to M, and a C of L over 2 plus J plus 1 up to N. And then I sync. So code is pretty straightforward, doing exactly what I said we were going to do over here. Analysis, a little messier. A little messier. So why? Let's just try to understand this before we do the analysis. Why is it that I want to pick the middle of the big array rather than the small array? What's sort of my rationale there? That's actually a key part, going to be a key part of the analysis. Yeah.
Because then you split the array A in half.
Okay.
Whereas if you're guaranteed, which is better than being guaranteed to split B in half because A is bigger. So
Yeah, imagine that B, for example, had only one element in it. Okay, or just a few elements. Then finding it in A might mean finding it right near the beginning of A, and now I'd be left, with subproblems that were very big. Whereas here, as you're pointing out, if I start here, if my total number of elements is n, what's the smallest that one of these recursions could be? N over 4 is the smallest it could be. Okay? Okay, because I would have at least a quarter of the total number of elements to the left here or to the right here. But if I do it the other way around, my recursion, I might get a recursion that was nearly as big as n. And that's sort of, once again, sort of like the difference when we were analyzing quicksort, with whether we got a good partitioning element or not. If the partitioning element is somewhere in the middle, we're really good. But if it's always at one end, it's no better than insertion sort. You want to cut off at least a constant fraction in your divide and conquer in order to get the logarithmic behavior. Okay? So we'll see that in the analysis. But the key thing here is that when we're going to do the recursion, we're going to have at least n over 4 elements in whatever the smaller thing is. Okay. So, but let's start. It turns out the work is the hard part of this. Let's start with critical path length. Okay, look at that, critical path length. Okay, so parallel merge sub infinity of n is going to be at most, so if the smaller piece has at least a quarter, what's the larger piece going to be of these two? Of these two things here. So we have two problems we're spawning off. Now it's a little bit, now we really have to do max because they're not symmetric. Which one's going to be worse? One could have at most 3/4, okay, of n. 3n, whoops. Of 3n over 4 plus, okay, so the worst of those two is going to be 3/4 of the elements, plus what? Plus log n. What's the log n? The binary search. Okay, and that gives me a solution of this ends up being n to the what? That n to the 0, right? Okay, it's n to the log base 4/3 of 1. Okay, it's n to anything of 1 is 0. So it's n to the 0, so that's just 1 compared with log n. Tack on, it's log squared n. So we have a critical path of log squared n. That's good news. Now, let's hope that we didn't blow up the work by a substantial amount. Okay, so the work is p m sub 1 of n is equal to, okay, so we don't know what the split is. So let's call it alpha. Okay, so alpha n in one side. And then the work on the other side will be p sub m of 1 of 1 minus alpha n. Plus, and then still ordered log n for the binary search. Okay, where, as we've said, alpha is going to fall between 1/4 and 3/4. Okay, how do we solve a recurrence like this? What's the technical name for this kind of recurrence? Hairy. It's a hairy recurrence. How do we solve hairy recurrences? Substitution. Okay, good. Substitution. Okay, so we're going to say PM1 of k is less than or equal to, okay, I'm going to make a good guess here, okay, because I fooled around with it. I want it to be linear, so it's going to have a linear term, a times k, minus, and then I'm going to do b log k. So this is this trick of subtracting a low-order term. Remember that in substitution in order to make it stronger? If I just did ak, it's not going to work, because here I would get n, and then when I did the substitution, I'm going to get alpha, I get a alpha n, and then a 1 minus alpha n, and those two together are already going to add up to everything here. So there's no way I'm going to get it bounded when I add this term in. So I need to subtract something from both of these so as to absorb this term. Okay? So I'm skipping over those steps. Okay, because we did those steps in lecture 2 or something, right? Okay, so that's the thing I'm going to guess where A and B are greater than 0. Okay, so let's do the substitution. Okay, so if Pm1 of n is less than or equal to, okay, substitute this inductive hypothesis in for these two guys. So we get A alpha n minus B log of alpha n plus A of 1 minus alpha n minus B log of 1 minus alpha, need another parenthesis there, 1 minus alpha n. Didn't even leave myself enough space here. Plus, let me just move this over so I don't end up using too much space. So B log of 1 minus alpha n plus theta of log n. How's that? You okay on that? Okay, so that's just substitution. Let's do a little algebra. That's equal to A alpha times alpha n, A times 1 minus alpha n. That's just A n. Okay, minus, well, the B isn't quite so simple. Okay, so I have a B term. Now I got a whole bunch of stuff there. I get log of alpha n. I have then this log of 1 minus alpha n. Okay. That's alpha n. And then plus theta log n. Did I do that right? Does that look okay? Okay, so look at that. Okay. So now let's just multiply some of this stuff out. So I have an minus b times, well, log of alpha n is just log alpha plus log n. And then I have plus log of 1 minus alpha plus log n. Okay, plus theta log n. That's just more algebra. Okay, using our rules for logs. Now let me express this as my solution minus my desired solution minus a residual. An minus b log n. Okay, minus. Okay. And now, so that was one of these b log n's, right? Is here. And the other one's going to end up in here. I have b times log n plus log of alpha times 1 minus alpha minus, whoops, I got too many. Do I have the right number of closes? Log of alpha 1 minus alpha, close that. Close that. That's good. Minus theta log n. And 2 ones there. Boy, my writing is degrading. Okay, did I do that right? Did I have the parentheses right? That matches, that matches, that matches. Good. And then b goes to that. Okay, good. Okay, and I claim that is less than or equal to an minus b log n if we choose b large enough. Okay, that this mess dominates this, because this is basically a log n here. And this is essentially a constant. Okay? And so if I increase b, okay, times log n, I can overcome that log n, whatever the constant is hidden by the asymptotic notation. Okay? So if I such that b times log n, b log n plus log of alpha times 1 minus alpha dominates the theta log n. Okay? And I can also choose my base condition to be big enough to handle the initial conditions, whatever they might be. Okay, so we'll choose A big enough. To satisfy the base of the induction. Okay? So thus PM1 of n is equal to theta n. Okay? So I actually showed O, and it turns out the lower bound that it is omega n is more straightforward because the recurrence is easier. Because I can do the same substitution, I just don't have to subtract off low order terms. Okay, so it's actually theta, not just O. Okay? Okay. So that gives us a log, what did we say the critical path was? Critical path is log squared n for the parallel merge. So let's do the analysis of merge sort using this. So the work is, we know already, is T1 of n is theta of n log n, because our work that we just analyzed was order n, same as for the serial algorithm. Okay? The critical path length now is T infinity of n is equal to, okay, so in normal merge sort, we have a problem of half the size, T of n over 2, plus now my critical path for merging is not order n as it was before. Instead, it's just over there. Log squared n. There we go. Log squared n. Okay? And so that gives us theta of log cubed n. Okay? So our parallelism is then theta of n over log cubed n. And in fact, the best that's been done is, n over, sorry, log squared n. You're right. How come I have log squared n? Because it's n log n over log cubed n. It's n over log squared n. Okay? And the best, so now I wonder if I have a typo here. I have that the best is P bar is theta of n over log n. Is that right? I think so.
There is something that is n over log n.
Yeah. That's the best to date. That's the best to date. By Ockel, I believe, is who did this for this. Okay, so So you can actually get a fairly good, but it turns out sorting is a really tough problem to parallelize, to get really good constants where you want to make it so that it's running exactly the same. Matrix multiplication, you can make it run in parallel and get straight, hard rail, linear speed up with the number of processors. There's plenty of parallelism. And running on more processors, every processor carries a full rate. With sorting, typically you lose, I don't know, 20% in my experience, okay, in terms of other stuff going on, because you have to work really hard to get the constants of this merge algorithm down to the constants of that normal merge, right? I mean, that's a pretty good algorithm, right? The one that just goes brrrr and just takes two lists and merges them like that. So it's an interesting issue and a lot of people work very hard on sorting because it's a hugely important problem, and how it is that you can actually get the constants down while still guaranteeing that it's will scale up with the number of processors. Okay, that's our little sojourn into parallel land, and next week we're going to talk about caching, which is another very important area of algorithms and of programming in general.